What happens when our machines learn faster than we can store their memories? We stand at a fascinating moment in history, a time when artificial intelligence is creating and consuming information at a rate that defies our intuition. These new digital minds are not just processing data, they are generating vast new worlds of it. They learn from immense libraries of images, text, video, complex sensor readings that map our world. Our current tools, the humble hard drives, sleek solid-state chips, are working tirelessly to keep up. But for how much longer? They are beginning to strain under the immense pressure of this exponential growth. Imagine an AI with memory not in gigabytes, not just terabytes, but in petabytes upon petabytes. Its digital consciousness sprawling across countless servers. A critical question emerges: where will all that data go? The digital universe is expanding, and our physical storage solutions are starting to look very small. This video will explore a potential answer: holographic data storage. This is a looming memory wall. The very progress we celebrate is creating the bottleneck of its own future. Artificial intelligence, in its current form, is a creature of data. It learns by example, and the more examples it has, the more nuanced and capable its understanding becomes. The large language models that now write poetry and code have ingested a significant portion of the public internet, billions upon billions of words. Vision models that identify a specific bird have been shown millions of images, each one a lesson in shape, color, context. Autonomous driving systems log thousands of hours of high-definition video and sensor data for every single day of testing. Making sense of these numbers requires a new vocabulary of scale. A petabyte is 1,000 terabytes, hundreds of thousands of HD movies, playing for more than a decade. The most ambitious AI projects operate with tens or even hundreds of petabytes. At global scale, needs are measured in exabytes, 1,000 petabytes. These numbers represent a physical reality, vast data centers, not clouds in the sky, but immense buildings filled with row after row of humming server racks. Webs of fiber connect them. They consume enormous power to run servers and to cool them. The iconic blinking lights are the visible sign of an invisible growing problem: immense energy cost and physical footprint. Where and how can we sustainably keep all these bytes for the long term? The data tsunami is here, and our current seawalls are not high enough. We have become skilled at building learning systems, but less at the logistics of their existence. A rethink is overdue. Our primary tools for storing this digital deluge are hard disk drives and solid-state drives. For decades, they have been the bedrock. HDDs magnetically alter spinning platters, a marvel of precision. SSDs trap electrons in tiny circuits. Faster, cheaper, more capacious, until AI's exponential data runs into physical limits. The first limit is density. Surface-based media add platters, add chips, or shrink features, but diminishing returns loom. Physics and heat at microscopic scales slow progress. You can't squeeze atoms or electrons without interference and instability. The second limit is durability. No storage medium lasts forever. Mechanics fail. Magnetic bits lose charge. Flash cells wear out. Tape is cheaper per gigabyte, but slow and fragile, prone to breakage and magnetic degradation over decades. The third limit is energy. Data centers are among the most power-hungry facilities. Storage and cooling draw massive, constant power. Backups, integrity checks, and migrations to combat bit rot add to the burden and to the carbon footprint. As AI's data needs skyrocket, the environmental and economic costs become urgent concerns we cannot ignore. We need more than incremental improvement. Beyond two-dimensional surfaces lies the vast potential of the third dimension. The answer may lie not in silicon, not in magnetism, but in light, crystal. This is urgent. Faced with the limits of surface-based storage, a new path is emerging, one that takes us into a new dimension. Holographic data storage offers a radically different approach, storing information throughout the entire volume of a material. Imagine a small, transparent crystal or a block of specialized polymer. Instead of etching a pattern on its face, precisely controlled light makes subtle, stable changes deep within its structure. These changes become the stored data, packing vastly more information into the same space. The fundamental principle is an elegant dance of light, splitting a single laser into two beams. One, the signal beam, passes through a spatial light modulator, encoding a page of data, 1,000,000 bits at a time, as light and dark spots. The signal converges with the reference beam at a specific point inside the medium. Where they overlap, waves interfere, creating a unique 3D pattern. That pattern triggers a photochemical reaction, forming a tiny permanent hologram. To read it back, shine the reference beam at the recording angle. The hologram reconstructs the original signal and its data pattern. A high-speed camera captures the pattern, reading an entire page in a single flash. By changing the reference beam angle or position, thousands of holograms can be stacked in the same volume without interfering. This volumetric approach achieves densities orders of magnitude greater than disks or flash. Writing and reading millions of bits in parallel promises incredibly high transfer rates. Light beats any mechanical arm. Optical access reduces heat and electrical resistance issues in conventional circuits. A leap to a new memory architecture. Well, that's the idea. The future of artificial intelligence will not be confined to a single domain. It will evolve across every field of human endeavor. In medicine, AIs scan entire genomes for minute anomalies and interpret complex medical images with precision. In science, simulations generate terabytes of output. In robotics, autonomous systems need long-term, high-fidelity logs. Each application fuels the data explosion. Demands become extreme. Future systems will need more than compressed summaries or curated datasets. They'll need raw, unprocessed sensor data. Multiple versions, different resolutions across modalities, creating dual pressure, extreme density, and extreme durability. Holographic storage can meet both, packing massive datasets into smaller footprints, ideal for permanent archives. Optical read-write accesses millions of bits in parallel, feeding multiple high-bandwidth streams, accelerating training, lowering energy per byte. This isn't just theory. Labs and companies are building demonstrators, combining holographic media with photonic chips and optical networks. Scaled up, data centers could look very different. Clean rooms of optical shelves, crystal vaults operated by lasers and lenses, changing storage economics. It's an exciting possibility. Personalized healthcare depends on storing a person's complete genome, lifelong medical history, and real-time sensors at population scale. Particle accelerators and next-gen sky surveys generate petabytes yearly. Holographic archives offer write once, read forever preservation. A holographic black box could store a robot's lifetime of sensory input, vital for debugging and safe learning from real-world interaction. No single technology is a panacea. Holographic storage is not a magic wand that will instantly solve every data problem. Significant engineering hurdles remain: scalable, low-cost, optically perfect polymers and crystals, precise, reliable lasers and lenses. New systems must integrate with existing formats, software, and networks, while robust error correction guards data for centuries. Manufacturing must scale from prototypes to global industry, a transition demanding immense investment and expertise. Imagine a secure vault no larger than a room, filled with crystal blocks holding the entirety of human knowledge, passively stable for 1,000 years. Picture AI training centers that are smaller, quieter, more energy efficient, datasets stored on compact optical media. Envision dramatically accelerated training as holographic storage feeds hundreds of parallel data streams simultaneously. The future will be hybrid: ultra-fast flash for active compute, tape for certain backups, and new memories yet to be invented. Holographic systems are poised to become the foundation for long-term, high-capacity archival. They can shift us away from fear of storage limits and toward digital permanence. Realizing this vision requires materials scientists, optical engineers, software architects, and standards bodies. Universities, startups, industry, and governments moving together. The stakes are high, momentum is building, and the road, though long, has a clear destination in sight. In the end, the story of artificial intelligence, algorithms, software, is also about physical limits, materials science, and the tangible consequences of our digital creations. As the machines learn, the bytes pile up, creating a weight our infrastructure wasn't designed to bear. Hard drives and solid-state drives brought us this far. We now stand on the shore of a new ocean of data and need a new vessel. Holographic data storage offers that bold path forward. It reimagines memory, moving from flat planes into the volumetric third dimension, using light to etch permanent memories into matter. It can hold datasets of unimaginable size in remarkably small spaces, not just for years or decades, but for centuries. This is how we build a library that can last for ages, through research, investment, and careful engineering grounded in imagination and foresight. We can build denser, more durable, more elegant vaults for our most precious scientific and cultural data. That future feels less like science fiction and more like a necessary and thrilling next step. This is more than just an upgrade. It is a new chapter in our relationship with information itself. For all of human history, our knowledge has been fragile, subject to fire, flood, and the slow decay of time. We can now write our next chapter in a medium as enduring as crystal and as fast as light. By doing so, we empower the AIs of tomorrow and secure the legacy of today. The future is bright, and it may well be holographic. Subscribe to the channel for weekly AI innovation updates and visit practicalaico.ai for practical AI tools and guides.